Hi, my name is Abhay Rawat, and in this video presentation, I'll be discussing a work titled Semi-supervised Domain Adaptation by Similarity-based Pseudo-label injection. Unlike unsupervised domain adaptation, wherein the task is to train a predictive model using labeled source samples and unlabeled target samples, semi-supervised domain adaptation considers a more practical scenario. In semi-supervised domain adaptation, or SSDA, the assumption is that we have access to a small set of labeled samples in the target domain as well. This access to labeled samples from the target domain should allow the model to better capture the relationship between the source and target samples, thus leading to better generalization. However, recent SSDA studies have shown that unsupervised domain adaptation methods cannot be directly applied in an SSDA setting. This is because aligning the source and target distribution with a small set of labeled target samples can bias the model and therefore lead to an intra-domain discrepancy. That is, the samples of source domain would be aligned to a small population of the labeled target samples. The unlabeled target samples, however, are going to be left behind, leading to the formation of subdistribution in the target sample space for each class. For efficient domain adaptation in an SSDA setting, we focus on reducing the domain gap while ensuring that a model learns a semantically meaningful feature space. For aligning the feature space of source and target domains, we use the supervised variant of the contrastive loss. We also ensure that a model learns a semantically meaningful latent space. We achieve this by the instant similarity loss, which encourages different views of the same sample to be closer in the embedding space. Furthermore, to mitigate the intra-domain discrepancy, we employ the intra-domain alignment loss, which pulls the samples that are similar in the target domain closer in a self-supervised way. We also propose to inject the unlabeled samples carefully to the label set of the target domain. This will help us to further reduce the skewed ratio of the number of annotated samples in the source and target domains. A feature level losses comprise of intra-domain contrastive loss, instance level similarity loss, and the intra-domain alignment loss. Sorry. In the following slides, I'll be presenting these losses and the intuition behind them in more detail. For cross-domain feature alignment, we use supervised contrastive loss. Only labeled and pseudo-labeled samples from both the domains are used for intra-domain alignment. Basically, we prepare positive pairs containing samples from each of the two domains and then apply the supervised contrastive loss. We should talk about the pseudo-label samples from the target domain in detail later in the presentation. Inter-domain alignment ensures that unlabeled samples from the same class in the target domain are closer together in the latent space. We achieve this by minimizing the L2 norm of the embeddings between two similar samples. Samples are considered similar if the indices of the top k highly activated feature dimensions are the same. The variable m in this loss equation denotes a binary matrix which indicates whether the ith and the jth sample are similar or not. Inspired by self-supervised methods, we ensure embedding for different views of the same sample are similar. Moreover, the similarity is computed with labeled samples from all the classes and both the domains to compute the soft pseudo-label for each unlabeled sample. Please note that the soft pseudo-label is a probability distribution for a sample, describing the likelihood of the sample belonging to a particular class. The model is then supervised to minimize the cross entropy of its prediction of a sample with the soft pseudo-label. We include local as well as global views of the samples in order to learn a meaningful embedding space, similar to a popular self-supervised learning method called PAUSE. The key contribution of our work lies in the pseudo-label injection method. In the previous slide, we discussed how the soft pseudo-labels are computed. We maintain a key value pair of the exponential moving average of every sample soft pseudo-label. These pseudo-labels are updated every time a sample is encountered during training. Every iteration, we check if the confidence or the likelihood of the pseudo-label for a sample is greater than a predefined threshold. If so, then we assign the label to the unlabeled sample as the argmax of the swapped pseudo label. And then we inject that data point into the label target dataset, thereby increasing the support of the label target set. We also remove previously injected samples if the confidence drops below the threshold. Here we present a brief overview of the SPI framework. Towards the left, we have the support set. In each iteration, the support set contains a predefined number of labeled samples from each class from both the domains. Note that the support set may also contain samples from the target domain that are pseudo-labeled. Along with support set, we sample unlabeled samples from the target domain as well. The computed embeddings from the support set and the unlabeled target dataset are then used to compute the losses. Here, H denotes the classifier layer and is trained using the cross entropy loss from the support set only. Soft pseudo levels are computed using the similarity based method that was described earlier. The key value pair mapping the samples to the exponential moving average of these soft pseudo labels are then updated. Lastly, we determine if a sample is to be added to the labeled target set or not using the threshold gamma. We also remove samples that were previously added to this label target set if their confidence falls below that threshold gamma. Here we compare the one-shot and three-shot performance of a proposed method with the existing approaches in the literature. We clearly see that a method outperforms the existing approaches in majority of the scenarios and also on the mean score. Next up, we show the performance of our approach in the 5-shot and 10-shot setting on the DomainNet benchmark. Here we can see that our method's performance on 1 and 3-shot setting are comparable to the existing approaches trained on 5-shot and 10-shot settings, and even outperforms them in certain 5-shot settings. This shows the efficacy of our approach, especially when supplied with large number of unlabeled samples. Here, we can see our proposed approach outperforms the existing approaches on the mean dataset accuracy on the Office Home benchmark. While we still see certain scenarios where our model's performance is less than the existing approaches, we posit that this drop in performance is due to the less number of unlabeled samples in these scenarios. Here, we present some qualitative results. We show the top 4 nearest neighbors from the source domain to the target domain sample. On the left-hand side, or the left column, shows the target domain, which is the clip art sample used as query. The other 4 columns on the right of each image denote the top 4 nearest neighbors from the source domain, which is real. Thank you. Have a nice one.